Energy stored in the system of charge. Given charge of a constant rho sub V0 coulomb per cubic meter, where R is between 0 and B meter. The problem is a spherical charge with radius of B meter. The charge density is constant. It means that the charge is distributed uniformly in the sphere. Find the energy stored in the system of charge. In the previous class, we derived two equations for energy shown here. We need electric field and electric flux density for the first equation, and need electric potential for the second one. We need to find potential V, electric field E, and electric flux density D. For the given charge, finding V from this equation is extremely difficult. We will find V from electric field instead. We need to find electric field first. We can find from electric flux density. Electric flux density D, we can guess the form of D from the given charge. It should be a function of the only one variable R, or radial distance, and its direction should be pointing outward from the origin, which is called AR, a radial vector. We can write the form of D as this. D can be obtained using Gauss' law. A spherical surface is used for Gauss surface to compute both sides of the Gauss law. There are two areas inside the charge where R less than B, and outside the charge where R greater than B. For R less than B, using Gauss' law, we need to find the charge inside the blue surface and the flux passing through the same surface. Then we obtain D in this area. For R greater than B, Gauss surface, the blue one, is outside the charge area. The enclosed charge is the whole charge. No charge from B to R. We do the integral from 0 to B. We find the flux passing through the blue surface. Then obtain D in this area. Now we have the solution for both areas. We can compute E from D. We have the E and D now. We can use the equation to obtain the energy. dV is this term. E dot D is these terms. There is no theta and phi dependent in E dot D. We can integrate d theta and d phi first. We got 4 pi. Replace this integral to the equation. It reduces to this. The limit r equal to 0 to r equal to infinity means that we change r from 0 to infinity. This includes two areas, r less than b and r greater than b, where the equations for E are different. We need to separate the integral to two parts. We need to choose the right equation for the right area. We replace E for R less than B in the first term, and E for R greater than B in the second term. Then follow the integration as follows. Finally, we obtain the energy. For the energy equation, we integrate the whole space, where we have electric field. Now, let's find the potential V from E. By integrating from infinity to R, we need to pay attention to the location of R. This integral equation means we find work for moving a 1 coulomb charge. Integrating from infinity means we have a 1 coulomb charge at infinity, where V is 0, to R, where R greater than B. Here is location of R greater than B. We move charge passing through only the region where R is always greater than B. For R less than B, we have a 1 coulomb charge at infinity. and move it to R where R less than B. Here is the location for R less than B. We need to move a 1 coulomb charge from infinity to B. Then we move from B to R where E is different. Here is E where R less than B, and here is E where R greater than B. We need to separate the integral into two parts as shown here. We need to choose the right equation for the right location. Then follow the integration as follows to obtain the result. Now we are going to compute V where R is greater than B. This is easier because we move charge passing through the only one region. Replace the right equation for E. Then follow the integration to obtain the result. Here is the complete solution for potential V for all regions. Now we can compute the energy from second equation. V dq means we multiply charge with the potential at its location. It is 0 where charge is 0. We then just need to integrate only where there is charge, or integrate from R is 0 to B. Since the charge density is constant, we can move outside the integral sign. The integral is only from R equal to 0 to B. We need to use the right equation for the potential V. We then integrate d theta and dv first. We got 4 pi. Then replace the right equation for V. Then follow the integration to obtain the result. This is the same as what we found by using E.d equation.